Hello everyone, thanks for the opportunity to present my research work in the 5th International Conference on Innovative Computing IC2022. My name is Khalil Rehman and I am the PhD candidate at Beijing University of Technology. So today my research paper topic is deep learning based approach for mammographic architectural distortion classification. This is the agenda and the content of this complete presentation. In the first part, we will discuss about the introduction and then literature review, research design, and at the end, we will discuss about the experimental results and analysis and the conclusion of the study. As we know, the breast cancer is the most striking cancer among women worldwide. The death rate was increasing from 6.6% to 6.9% as per World Health Organization report all over the globe in the year of 2020. The early screening of breast cancer in women can decrease the death rates. So the mammography is a standard screening method for the early detection of breast cancer in women. So the automatic detection of breast cancer from mammograms using computer algorithms at early stages could help doctors to avoid unnecessary biopsies. Architectural distortion is the third more commonly detected abnormality in digital mammograms among the mass and microcalcification. So the manual tracking of architectural distortion for radiologists is a challenging due to its subtle appearance on denser breast tissues. A very limited number of studies reported in the literature which performs mammogram classification based on architectural distortion using machine learning algorithms. For example, the author 5 present a machine learning based novel algorithm to detect architectural distortion from mammograms and achieving 0.90 sensitivity. Another author investigated in several cancer cases in detecting sites for architectural distortion using machine learning approaches and also reported 0.90 sensitivity and evaluating the private datasets. Such problem. In recent years, the deep learning algorithm consistently performs better to increase the true positive rate of breast cancer prediction than the traditional machine learning algorithm. The previous studies showed that detection of architectural distortion from digital mammograms using traditional machine learning techniques was challenging due to its tiny size and subtlety. These methods successfully detected the architecture distortion (ROIs) region of interest from digital mammograms while achieving very low sensitivity rate. So in this study, we investigated the limitations of using computer vision based deep convolutional neural network. So we proposed a novel computer aided diagnostic system classifying architectural distortion (ROIs) using computer vision algorithm and the classification with the bitwise convolutional neural networks. The proposed method pertains to the three steps: image preprocessing, architectural distortion (ROI) extraction, classification of architectural distortion (ROIs) into the malignant and benign classes using the depth-wise convolutional neural network. Figure 1 presented the proposed framework of our computer-aided diagnostic system. So here we can see that we call it the digital mammograms, and then we have to pre-process these mammogram images to extract the region of interest by by using the computer vision algorithm. And after that, we will train our deep neural network, that is actually the depth-wise convolutional neural network, to classifying the malignant and benign ROIs. We also compare our proposed method with other well-known sport vector machine and k-nearest neighbor machine learning algorithms. For achieving our goal, in this study we included two data sets. The private data set that we collected from the local Peenam hospital in Pakistan, the Pakistan Institute of Nuclear Medicine and Radiology, and the public digital database screening mammography, which is publicly available and provided by the University of Florida. The Peenam dataset includes 577 original mammograph images, from which 425 benign and 152 malignant images. The DDSM dataset is publicly available dataset which contains about 2,600 patient cases containing masses, calcification, and architectural distortion related studies. We acquired 3,568 total digital mammogram images from the DDSM datasets, which contains 1,740 benign and 1,828 malignant images. For training the deep neural network, there would be required a large number of images for training and testing and the validations. For our public dataset, we have enough images to train the neural networks, while for the local genome dataset, we have very small types of images. Therefore, we should implement some data augmentation techniques such as the vertical flipping, horizontal flipping, rotating, and zooming functions onto the genome datasets to increase the size artificially. So the images are rotated on 35 degree, 45 degree, 75 degree, and 135 degree to obtain the four rotated images with one original image. The zoom in technique was implemented with the ratio of 0.6, 0.9, 1.12, and 1.15 to keep the original pixel values of the images. The dataset increased up to 2,885 images. So we included the region of ROI images extracted using the image pixel-wise segmentation from the digital mammogram images. The area has a star-shaped pattern we considered as an architecture distortion ROI and segmented into the pixel array using the computer vision algorithm. So each pixel that is belong to the star shape has a specific class label with the M and N, where A is an array having a pixel of M and N, then corresponding label we have A belongs to M and N number of pixels, that is belong to specific class of P, Z for the benign and 1, 0 for benign and 1 for the malignant images. The segmented ROIs after that put into the deep neural network for classification. The traditional deep convolutional neural network has single color channels for training the images, which actually reducing the sensitivity and also increasing the computational times. So training the images with a single channel was not limitation for the neural network, but it decreased the network performance. Therefore, we have the fully connected depth-wise convolutional neural network that employed each depth of a color channel to train the network. We developed a network like VNet64 architecture, which consists of three convolutional layers, three polling layers, and two fully connected flattened layers, as we can see in the table. This is the layers, output image, filter size, and number of total prompts that runs after each convolution, and their output results. As we can see, the convolution layers, activation, RLU, maxi pooling, convolutional layer, and then max activation and max pooling, and at the end, two flattened layers, fully connected flatten 7 and fully connected flatten 7, and after that, the output layer. In this network, we use the sigmoid net classifier as a classification. Experimental result analysis. Experiments of this study were carried out on three models, such as the proposed and the other well-known machine learning SVM and PNN for the evaluation of our both local and the public datasets. We datasets split into the training, testing, and validation with the ratio of 60%, 20% for testing, and 20% for validation, with the five-fold cross-validations. Figure 2 and Figure 3 reveals that the training loss consistently decreasing and accuracy increasing on both set datasets, which means that the noise around the data are very low and our model is well trained, not overfitted, and well regularized and generalized. So the experimental results demonstrated that our proposed method achieves a higher sensitivity rate than sport vector machine, pioneer snuggables, and the previous studies. Figure 4 and 5 present the sensitivity comparison with these two well-known algorithms. Here we can see that figure 2 and figure 3, the training loss and training accuracy on both datasets after the seventh epoch, we can see that the training loss consistently decreasing in the Phenom dataset and on the DDSM dataset after the 10th epoch, it is also decreasing, and the training accuracy increasing and reaches up to 100%, which means that our proposed network is perfectly fitted. Here some experimental comparison of the sensitivity with other networks. We can see that our proposed model achieves 0.99 sensitivity, while the other two only achieves 0.96 and 0.98 on premium datasets. On the other hand, our model's performance is very well as compared with other networks on public datasets. It achieves 0.95 sensitivity, while other two only achieve 0.79 sensitivity. For the evaluation of models, we also calculated the area under the curve with our proposed model, and which was also higher than the sport vector machine and PNN, as shown in figure 6 and 7 in next slides. So we also compare our studies with the previous studies. So table 1 shows that the proposed method of our obtained method is higher than the other public and private dataset using by the previous studies. The proposed method has obtained 3%, 1%, and 16% and 16% higher sensitivity rate than the sport vector machine KNN on Phenom and DDSM datasets. From the all experimental results, we can see that our proposed model outperformed as compared with the machine learning algorithms and the previous studies. This is the area under the curve, and if we can see that our proposed model achieves 0.86 area under the curve on DDSM dataset and 0.82 on the Phenom dataset, while the other two networks has very low area under the curve, which means our model performance is much better than the other machine learning algorithms. So here are some comparison with the previous studies. As we can see that on the DDSM dataset, the maximum achieved sensitivity was 0.90 by after 6 minimum peak at all, while we can achieve 0.95 sensitivity on DDSM datasets. And if we can see the maximum gain accuracy on DDSM datasets by the previous study was 0.93, which was still lower than our proposed method. And similarly, if we can see that private achieved accuracy on private data sets by the SBNIC was 0.90, while we can achieve 0.99 sensitivity on the local genome datasets. So at the end, we concluded that architectural distortion is the third most suspicious of normality in denser breasts, indicating breast cancer in women. So the manual recognition of architectural distortion for radiologists is challenging due to its size and varying symmetries inside the breast. Therefore, the early detection of breast cancer is very important for the detection of breast cancer. So in this study, we propose a novel automated computer-aided diagnostic system to detect architectural distortion from digital mammograms using computer vision algorithm and deep convolutional neural network for classification at early stages. So our model uh, should perform a comparison of results on two data sets. One is the public data set, and the second one is from the primary source of data that we collect from the local hospitals. It could help in real scenarios in daily clinical routines to improve the diagnostic ability using the computer algorithm. So experimental results shows that our method, the proposed method, achieve higher sensitivity rates from the sport vector machine, ANN, and other studies. Which means our proposed method has better performance as compared with the previous study. So this is the complete uh, presentation on our paper that we present in the fifth International Conference on Innovative Computing IC 2022. So thanks for the opportunity. Thank you. Have a nice day.